Okay. So this is the traditional way, right? There's some data that's coming. We are doing some operations using the data, and that's causing state mutations. So this will be the code that would be running for this. Okay, I will be taking a few code examples so that we get the feel of it for people who do not like know exactly how it is in the reactive space. And I will go into the like why do we need reactive, and how is it different, what problems are we solving, all those things. So it's a pretty big presentation that I will prepare. It's 30 page something. So you can see that we are creating a turbine, then we are calling a method on it. We are going to generate some power, and then we are going to return that power. Okay. And you will be seeing these terms like non-reactive, pull-based, blocking. So I will be explaining the meaning of these things. Pull, what is pull, and what exactly is blocking, what is not blocking. Okay, and this would be the batched version of this. We are taking a list of power or water, and then we are going to return a list of power. I hope this is pretty clear. Now, just to give a introduction to this, what difference we are implementing here is we are taking the data and the operations that we saw in a previous photo, and we are just going to take that into a logical whole called stream. And there are various names by which we call this stream in different libraries, in different languages. For example, in Spring Flux, we call it the Flux. And then we have the Java 9, JDK 9 flow. And then we have also the Reactive X or the RX Java observable. All of these they are more or less, they are the same thing. They are, and how they are the same, I will just go into the next slide. Okay, and why we have made these new abstractions. So we can, as we will see, there are certain problems that are better explained or better solved at scale using these abstractions. That has been the evolution from the traditional model. And you can see that as I go into the next slide, probably it would be better to go right now. So you can see this is the reactive version 1. Okay, I created a turbine which I got, did not get a turbine. In fact, I got a mono of turbine. And then I mapped it to a particular function, and then I again mapped it to something else, and then I returned that particular mapped thing. Okay, what thing is that? It's right now it's a flux, and you can think of this something like a future or a promise or these observables that I was talking about. Okay, or these flow. Okay, and why is this? Now you can now I come to my next point here, which is how is it declarative as opposed to imperative. So if you see the differences in the codes of previous here that I showed you, okay, you are doing it imperatively, and here it is more declarative. You are changing, transforming, and it feels more intuitive in a sense. Okay, you have to read the code here. So you have to understand the code, what is it doing, but you have to understand the code here also. But there are certain standardized operations that you're doing. For example, mapping, filtering, okay, merging, concatenation. All these things are very, very standard in terms of streams when we talk about. So since you are using those paradigms very frequently, you are creating a new language or new abstractions to describe your code. So that gives it a more declarative syntax. And you can see the code here also, the error handling that we have done. So that was also one of the things. So we have try catch we have here in this non-reactive code, and here we have on error resume. So this is a different way how we handle errors in the reactive world, and why that is required. I will go into that also. Why? Because we are actually doing it in async way. So that is why normal blocking try catch doesn't help that much. It creates more problems. So that is why error handling has been incorporated in the as a part of the reactive design. So that comes to my next point, because try catch is not really adequate for handling errors in async flows. When we are not talking about a single thread going through the entire flow, what we are saying is, when we are going through multiple pieces of code, the threads may change. Okay, so and why that is required, I will go into why we can't be using a pure per connection per thread model. Uh, that is what the traditional model is. Okay, then there are other things. It's event based as opposed to thread based. That's what I was saying. And why it's event based, I will go into next. Okay, so this is the reactive manifesto. It's a design paradigm, how to build systems that are reactive. Okay, so there are four major cornerstones. How we can do that: responsive, resilient, elastic, and message driven. So any systems that we define or design, is they should be and there are broad uh, guidelines how to achieve these things. So responsive, what this means is that we should ensure rapid and consistent response times. There should be a predictable way in which our system is giving us responses. That is very first and the most important probably. And how we are going to achieve this responsive behavior in our designs is why our thread model is event, why we are going for event based, and why we should use async flows and non-blocking code instead of blocking code and uh, in same thread semantics. So why we are doing all that, because we want to achieve this. Okay, then the second thing that uh, is there resilience. So it means that in case of a failure, our system should still stay responsive. And why, how we achieve that is by replication, isolation of our system components. So what points I am here describing, they actually are not just applicable for individual code pieces or modules in our code base, but instead they also uh, have been into the picture for different architecture designs. When we define certain architecture, we have a queue, we have a JVM running, we have a pool of servers, and we are reading from a database. So how we should manage all that. So all these things, they are applicable there, and they have been for long. So this is the cornerstone how we do uh, high availability in databases like Cassandra, ring-based topology. So the ideas are the same, but what reactive programming tries to do is that instead of just um, be limited to these things on the broader system level, it tries to incorporate those in the code level as well, in the individual modules or the individual classes or methods. There also these things apply. So you can just understand this in a way. What I'm just going into the next page, I will come back to this slide. So maybe anybody of you may have seen this before, right? What are fractals? Fractals, they are system structures which have a specific property. So that the property is that they are self-similar, which means that what you see at the at 20,000 feet is the same as what you see at 1 nanometer. So when you go into the deeper parts of the fractals, you see the same structures repeating and again. And that is what is happening in the other structures found in nature. Mandelbrot set is just a mathematical set, but Romanesque broccoli, which I have shown you on the left hand side, this is a nature, this is a vegetable actually. So what we see is that fractals are very common in nature. Okay, and this is what has been observed, that since nature has a way of optimizing things, okay, and we see such patterns everywhere. So I am not sure about the mathematical framework to explain this, but intuitively it makes sense if the internal lines, the internal designs and the external designs, the macro and the micro pictures, if they converge.
It's called
So
construction theory, right? Right now, where
maybe,
everything is like a subset. I mean, the design is same, and
yeah,
only in terms of complexity, it is different.
yeah. So if you like magnify one part of the fractal, you will find the same pattern. Similarly, in this design, what we are talking about, responsive, resilience, elastic, message driven, all of these have been implemented in system design. But reactive programming, it takes to the micro level, all of these things by using streams. Okay, so the rest of two of them are elastic and message driven. So elastic means under varying workloads, the workload is very high or very less, it still stays responsive. Okay, message driven means that we have to ensure loose coupling between the different components. So that is why we have these async message passing, and thereby, if we are doing message driven, we can also do flow control. Flow control is a very separate topic. I will go into it. Flow control is essentially how we manage the varying speeds of data interaction between two components. One component may be producing data very fast, and the other component which is consuming it may not be able to keep up with it. So those kinds of scenarios we take care by flow control. Okay, this is one of the slides taken. Okay. Okay. So how the evolution of reactive programming happened? Yeah. So we had JavaScript in the very beginning, 1995. Then we had Nginx, and these things, they have been going on for such a long time, but the ideas, they have remained similar, and they have been built on top of each other. After Node, we got reactive extensions, which is the major breakthrough. Okay, and here reactive extensions is the first framework where we actually got to glimpse the current reactive paradigm. And then there was akka, and then there is neti. Neti was extremely important in the development. This is a library. It's something like a runtime for building servers, and it has these event-based and non-blocking asynchronous, all these features. Okay, on top of Neti, then various other things started to build. So you see, after 2012, it just kind of exploded. So many things are coming up. So 2013, even just we have so many things coming out. Then 2014, and then 2015, 16, 17, and now we are in 2020. And you see how important it is, because this idea was incorporated into the JDK 9, and none other than by Doug Lee himself. So you can see why it was done, because they wanted these things not to be just from some third-party library. They wanted to standardize it. So the entire idea of Java, of these observables and everything, they put it into JDK9. And Spring Web Flux is the one very important uh, uh, part of this ecosystem. Currently, everybody who is into the space either uses Vertex or Spring Web Flux, or there may be Ratpack that is also there. And RX Java is extremely important, which came out in 2013 also. So RX Java is another library which gives all these features of handling observables. Okay, and it is there in for multiple languages, not just Java. So the RX specification, that the Reactive's extensions.NET 2009 specification, so whatever was there, it was implemented for multiple languages, and Java, JavaScript. We have reactive wrappers in the form of RX prefix for almost all of the languages from there. Then came the Reactive Stream specification in 2014, and Reactive Stream specification is amazing. It's just a one-step iteration of the reactive extensions. It adds certain missing things over there, and consequently all of these other libraries, the Project Reactor, Vertex, Netty, they have implemented those features of reactive streams, the additional ones. Okay, and why I have tried to show it here is because we can see the initial ideas of asynchronous event-based non-blocking programming, they were there, but once we stepped onto the into the millennium, we saw explosive internet traffic. Okay, we had to scale our servers. Only then these things started to get built, and that takes us to the C10K problem. So I will just describe it a little here, and then I will go back. So the problem of C10M is that we have to scale a single server to handle 10 million connections concurrently. This was one of the challenges that was thrown out in the early 2010s. Later 2010s. So first it was C10K, then it was done, and then C10M came. Basically, just an excitation. So how it's possible? So there are two things here. First thing is we have to understand that handling many requests per second does not constitute the solution for this problem, uh, which is processing them very quickly. So if we are processing very quickly a lot of requests, okay, it's not the ask. Now high throughput is not the ask. It is the ask is that we have to maintain a lot of concurrent connections. So that requires lots of thread contention, and that actually is a scheduling problem. So we have to uh, maintain these concurrent connections live, and we have to still like accept more connections up to that limit which we are talking about. Okay, and what was seen as a baseline was that a particular thread in a 64-bit VM is taking probably 1000 KB stack size. So if you calculate by that assumption, then for 64,000 requests in a thread per connection model, which means that one request comes, it consumes a new thread. So that was the original model, right? Our blocking model, which was done in Spring MVC and before Servlet 3.1 implementation. Okay, Spring MVC and Apache server. So a new thread is allocated to a new request. So that would take up 64 GB of memory, which is highly infeasible because that is not a way to scale. So the problem remains unsolved by using this model. If we use a single thread for a single request, every thread takes a new request. So so how we came to the solution? We found a solution in event-based programming, which revolves around an event loop. So it is essentially about using the same thread for solving many of our requests. So that is the way we how and what is that pattern? That pattern is called reactor pattern. Okay, and for understanding the reactor pattern, we have to understand the observer pattern. So before that, I will go into the observer pattern. So okay, so first event-based programming. So event-based programming is uh, when we have uh, lots of things that are happening in our program, okay, and we are using a listener model. We fire certain events, and then the places that the listeners that we have, they respond to those events. So if we press a button, so this particular will generate an event called press this button, okay, and something would be listening for it, okay, and that would be doing the associated action for that. So this is simple event-driven programming. Okay, and our reactive programming is a special case of event-driven programming. So we don't do it in blocking way, that we just give me now the response. Okay, this is done now. Now do this one. Do this at the same time. No, we just say okay, some action has happened, some event has happened, and in some later point of time, asynchronously, maybe in a separate thread or in the same thread, this action, related action of this event will be happening. Okay, so the observer pattern is a very simple pattern. We have observers, okay, we have subjects, and we have events. So it's simple notification pattern. We are listening for events, okay, and observers observe method is called whenever an event occurs. So observers come first, they register themselves in the subject, okay, and the subject will be getting the events and then calling the observe method of the observers. That's the subject observe pattern. Okay, so you can understand why we are doing it this way. This is decoupling the event production and the actual event consumption. Okay, in a traditional way, we would have called the events on directly on the observers. We wouldn't have this abstraction in middle. Okay, then the pub sub pattern. This is also a related pattern, and we will see this and how this is related to the observer pattern. It's a common pattern in event-driven applications, and there is a channel in between which is mediating between the delivery of the event. So the publisher, so we have changed the nomenclature a little bit. There is a subscriber now, a publisher now, and then there is a channel. The channel will be getting the events, and the events will be then just given to the subscriber who is subscribing on the event channel. All of these is still abstractions. We will see a little bit how it comes into our picture. Okay. So, so I showed you the diagram, right, where the reactive X, in 2009, reactive extensions, they came out, right? So what they were actually, we will start from there. So reactive extensions, it's a set of tools which allows us to work with streams. Okay, and it's a combination of the observer pattern. Okay, and basically what it does is that it abstracts you away from synchronization, thread safety, and concrete data structures, because it's trying to use a single thread to do everything. So what that means is, if I go to the event loop, so I told you about the C10K problem, right? And how we were uh, stuck with that model in which we were consuming one thread for one connection, for one request, for we were using one thread. So the only way to get around that problem was to reuse the same thread. Okay, which is actually what happens in NIO, or the non-blocking IO. In the Apache Tomcat, if you see, uh, there is a way in which we can configure this. Okay, similarly, the event loop takes it one step ahead, and what it does is that you have a fast spinning thread, okay, and what it tries to do is whenever you are having some event, okay, it is trying to just register those events. For first, there is the registration process. Okay, so when your program boots up, the event loop has got registrations for all kinds of events that would be occurring and what to do when those events would be occurring. Okay, for example, when there is a uh, new request coming with this particular endpoint, then this handler has been registered for that particular event. Then Y handler has been attached for when the data comes from the database. All of these things we have already registered in the event loop. Okay, these are the event handlers that I was talking about. Okay, and when the actual data comes into our application, so that will be evaluated what handler it is corresponding to. Okay, that handler will be called. Okay, and it may be called in the same thread or it may be called in some kind of worker thread. Okay, and the internals, how that notification is coming, that is all happening asynchronously or in a non-blocking fashion. So what I mean by is a non-blocking action. If I come to this, yeah. So what happens is that whenever we have to do certain network activity, let's say, or we are reading from a file, or we are basically we are dealing with sockets, right? And the socket is in any kind of a Unix system. We model them as file descriptors. Okay, so every socket is essentially a file descriptor. Whenever some data is coming or data is going, that is always happening through the file descriptor that is at the kernel level. Okay, and how we do that? So let's say there was a connection. Okay, a user tried to make a connection with our VM. Okay, so what it will do is it will try to connect with some port. The port is actually mapped to some socket. Okay, and our kernel would be asked that this connection has initiated. So some code will try and give this file descriptor to the kernel, and kernel will tell it that, okay, there is no data as of now, check back later. Okay, and this code, it will poll this particular file descriptor again and again at the kernel level, asking for more data. Okay, that was the case when epoll was not there. How we get data from the kernel from the socket. Uh, so when the data arrives at the socket, okay, kernel can tell us in two ways. The first system call is called select or epoll or poll, and then the other one is epoll kq ioc. So these are the system calls which are used whenever there is a data available to read or write on a file descriptor or a socket. Okay, and what I was initially going on about regarding fractals, right? So you can see there also we are doing the same thing, and even at the kernel level we are doing the same thing. So we are actually reactively handling these notifications at kernel level. So right from kernel level to code level and then to the system design, we are trying to follow those four principles. And that is why we are saying that this is non-blocking behavior with epoll. So in a nutshell, epoll, you can use it to get notifications from the kernel for a change in the file descriptors status, that it is ready to read or write. And with select poll, it was a blocking behavior. You give the kernel a list of file descriptors and it will return those which are ready with data, and that's it. It will not remember those file descriptors. And once you do this again and again, and you have lots of sockets, like what I was telling in the C10M problem. So if you have 10 million sockets, okay, 10 million file descriptors, you give the kernel all these file descriptors, and the kernel has to go through all of these, okay, and it will try to find out, okay, this is ready for read, this is ready for write. So at that point of time, when it is too much, the number of sockets has become 10 million. This whole activity of iterating over the file descriptor itself is very, very huge compared to actually uh, getting the data from the so the kernel will, most of the time of the kernel or the CPU will be spent in that only. That is why it becomes slow then. So instead of that, what we are doing here is now we are using epoll, okay, and what it does is it will notify you. First you give the list of file descriptors to the kernel, okay, it will create a red black tree inside, okay, and it will notify you whenever the file descriptors are ready with data. You don't have to uh, it is much more efficient that way. So so this was the internal implementation of a non-blocking input output. Okay, we don't have to care much about this, but this gives us an idea of how we are taking the same concepts which we have been applying over the system design and going deeper into the system. Even at the kernel level, we are doing the same thing.
Zafar, can you talk about, can you go to this slide where you have a circle, this one? Can you talk about this a little?
Yeah. Okay, so right, so basically what we are doing here is we have the event loop, okay, which is a set of server, a set of threads. Okay, why we are calling it a set of threads? Okay, so in contrast, if you have worked on Tomcat and the traditional non so blocking implementations, you will have a thread pool, okay, a connection thread pool, and anytime a request comes, it will be given one new thread from this particular thread pool. Okay, but here we don't have that concept. We have a small set of threads which we call the event loop threads. Okay, for example, and in general they are like something like uh, twice of the number of cores in your server. So if you have 16 cores, then it will be 32. So 32 threads in the event loop and event loop thread group. Okay, and you would be having requests. Okay, the requests would be coming and they would be putting into a acceptor thread queue. Okay, and then the event loop will be taking these events from this queue. Okay, until if there's nothing, then it will just stay blocked. Okay, and let's say there is some event that is coming, then it will take it. Okay, it will execute it. If it's a CPU intensive work, then it would give it to the worker threads. That's the model. And why I'm calling CPU threads going to be executing the worker threads. So you see, one important thing that we have to take care is that this event loop is spinning very fast. It has lots and lots of events that it has to handle. We don't want it to be blocked for a while. If we do certain blocking activity in an event loop, then the entire purpose will be defeated. So that is why whenever there is some kind of a blocking activity, there is another something like file read, for example, something like you are sleeping. Okay, so all these things, they should not happen in the event loop. They should be happening in the worker thread. So and why we are using and how it's actually optimizing our entire flow, because we are using a single thread. We don't need synchronization. Okay, we have basically saved on these 64 GB. See, lots of connection threads will be consuming 64 GB. So we have resolved that problem. Okay, and since we are doing it in the in one thread, in one event loop, we have uh, everything happening and combine that with the non-blocking CPU or the kernel behavior, that actually increases a lot of efficiency because of less CPU usage and also less memory. Actually, there have been multiple like tests for this particular thing, how this CPU and memory, is it really actually happening in the real use case, and there have been multiple use cases where it has been found that under very heavy load, or even moderately heavy load, blocking code or normal traditional per connection per thread, we have a much more higher improve efficiency in both memory and CPU. Okay. So now coming back to the ReactiveX observer pattern. So the observer pattern, how we have implemented in the ReactiveX here is, okay, we have added two things to the actual observable thing. So in the actual observable, we had these things, right? We can subscribe, okay? We can get the notification. That's it, okay? Now in the ReactiveX, we have added this thing that the producer can signal that there is no more data available, okay, which is on complete, right? And then the producer can also signal that an error has happened. So these are the major contracts of the ReactiveX. So basically you will have an observable, okay? And this observable is the intermediate entity which is acting between an observer and a producer, right? So the observer communicates with its observable by means of notifications like subscribe, unsubscribe, request, okay, and observable has on next, on completed, on error, and on subscribe. So basically you have the observable object, okay, and you call these methods on next. What happens when on next happens? Basically when a new message comes, then the on next will be called, okay. When the stream has finished, on completed will be called. When there is an error, then on error will be called, okay. And similarly we can request multiple items from the source. So observer communicates using subscribe, unsubscribe, and request. So the starred items here, on subscribe and request, both of these have been actually added later. They were not part of the ReactiveX contract. They have been added in this one, the reactive streams specification. This came later on and it added these two new things. Okay, so we have probably a fair idea on how we are interacting.
So Zafar, is it safe to say that we are kind of bringing the concepts of pub sub model or asynchronous model communication, which we normally apply at the between the applications and and
yeah, exactly
bringing those constructs to the language level and to the OS level.
Yeah, we are coming it to the micro level. We have taken those concepts and we have implemented them at the modular level, even at the code base, like class level. So that is how reactive programming, what it means actually. So now comes the major problem that we were trying to solve initially, right? Flow control problem. So basically, if you have an infinite stream of messages, okay, then there can be two kinds of problems. So there is a producer. We saw the pub sub, right? So there is a producer which is producing messages and consumer consuming messages. Okay, and consider a case when the producer is very slow and the consumer is very fast. So basically, we are not utilizing our system. The consumer will remain idle. Okay, a lot of time. So basically we have to then scale the producer. The consumer will remain idle. So if we have lots of producers in that case, consumer will still pick up and utilize, right? So that is one aspect. The other aspect is we have a fast producer but a very slow consumer. Okay, so the messages are being produced extremely fast, but the consumer is not able to keep up. That is the more seen scenario. Okay, and how we solve it today? We have three ways. Okay, we let it queue basically. the producer is producing messages. At the consumer level, we have a queue. We queuing the messages. Okay, but if we have the queue as an unbounded queue, basically without fixed size, then the queue would be going out of memory, right? And after some time, our consumers will die. So this is not what we can do in the production systems. Similarly, the second solution is that the queue can be throttled after a while. I mean, they keep a fixed queue, but let's say the queue gets filled. Then what happens? We will throttle. Okay, basically we will drop messages. So, but we cannot do this for critical events. Why? Because critical events like, let's say, banking or these things, they can never be dropped. If they are dropped, then it will be a loss. So, and then the third thing is that we can have a queue. Okay, we queue it, but once the queue is full, we will block the next messages. So basically, producer will not be able to produce only. Producer will be blocked. So basically, in our entire design, the slowest consumer will be just blocking the entire system, right? So its throughput will be the overall throughput of the system. So this is not, these are the three ways in general what we solve. Okay, and then there comes the reactive solution, which is using back pressure. Okay, so back pressure is an extremely important concept, and why? Basically, it's related to scalability. Okay, and how we solve it in reactive world is this. Okay. So basically, this problem was faced, and then came the reactive strain specification, which is 2014. Okay, and what they tried to do was actually solve this very problem, that if there is a very fast consumer, very fast producer, and a slow consumer. So what they did was that they have made such new abstractions, okay, in which, by using which, we can signal back to the producer that you are going very fast, or we can do other kinds of stuff. But there is an abstraction now which we can handle it. We don't, this is not just one way communication that producer is just producing and consumer is just consuming. Oh, I'm being overwhelmed now. No. So they have made a communication channel. Okay, this is a abstraction that we have got now. So okay, right. So basically, uh, you can see that in that reactive contract also I have written, right? Here, right? There is a request method, right? So the observer communicates with its observer by means of these notifications. There is a request method. So this request method gives us a leeway now. We can request only certain number of things. Okay. So consider this scenario where we have a service and a database. Service is asking for some items. Okay. But initially it was something like, okay, get me some item. The database responds. Okay. Again, service says, okay, get me some item. Database responds. In that case, while database is processing, service remained idle, right? But in our reactive world, what we can do is we can subscribe to the database, okay, using reactive programming, and database will continue giving responses later on at asynchronously, okay? So that way, our service thread will be free as compared to the initial case when we were just getting one item, one response, one item, one response. Okay, and now back pressure, what it tries to do is we have the method called request, in which we can ask for a certain number of requests. So if the service is feeling overwhelmed, okay, then it will ask for a limited number of items only. So it will ask for one item or two items. But if it is very free, then it will ask for more number of items. So there's the request method. You can see 10, right? So 10 is the number of items that has been asked. Okay, so this is in the control of the consumer. Consumer can now set its own rate. Okay, and there are other things as well which we can do by using this back pressure. This is called back pressure. When we can control the rate from the consumer side. Okay, Now this is one very important concept in entire reactive programming, pull push. Okay, and you will see this term many times. Okay, so so I've tried to give a certain analogy here so that we can understand better. Okay, so you can see in pull we have this. We are spinning a particular thing, right? And we are pulling weight. Okay, we are pulling weight just as in we are pulling water from a well. And in push, what is happening is the opposite thing is happening. The uh, glass on the left, it's pushing water to the glass on the right. Okay, so so how reactive is different. So in general, what we used to do in the traditional way it's a push mod. It's a pull once, push once model. So we ask for an item that is called pull. Okay, and push, it gives us that item. So that is pull push. But pull once, push once. Okay. So you got it right. So we call a method, okay, on any object, okay, with an argument, and we get the response in the same thread, right? So this is the pull once, push once, right? But in reactive, we subscribe, we do it asynchronously. So we pull once, but we get many items in return, right? So the reactive is pull once, push many. Okay, in shorthand, many times you will just find either pull or push, not pull once, push many, something like that. So basically, when you just get pull, it means that pull once, push once. If you see push, it just means pull once, push many, which is reactive. Okay, and I will try like to because many of like most of us probably would be aware of the Java 8 streams. So Java 8 streams is not reactive. Okay, it is a pull once, push once model. We create a stream of particular. Let's say we have our array. Okay, we create a stream. Okay, and we consume it because we have defined everything. It's not an infinite flow. It's whatever we define as the first item, as the number of items. Only that many will come later. So that is why we call Java 8 streams to be a pull once, push once model. There is no back pressure. There is nothing, or all of those concepts which we mentioned earlier. So, okay, now we come to the other reactive concept called hot cold streams. So you will also encounter this term. So a hot observable or a hot stream is a stream which has been created at some past date maybe, and it's just going on and on emitting items. Okay, and our observable may start anytime in between. Whenever it subscribes, it will start getting the items. But the cold observable, it has been like it has not. Whenever we subscribe to it, it will give it from the first time. So this is what's the definition. Basically, in Java 8 streams, we have a cold observable. So whenever we define something, it is static. It doesn't change in the middle. Okay, so if we have to implement reactive in our use cases, we have to go apart from Java 8 streams, probably into RX Java or Vertex or all those things, right? So, okay, so we have covered almost all these things, right? Now, yeah, so this is what I was explaining, right? So you can see in order to, if we have a system, okay, we have all these components happening, right? There is a filter map, then there is a sink, there's a source. We have asynchronous boundaries in between in the form of a queue, okay? And basically the reactor pattern or the event loop that we discussed, that is also a similar construct. What it is doing is it is making these queues that we see, right? These would be now handled by our event loop. So and why this is beneficial? Because we see that the creation of threads, okay, and all those consumes resources, okay. So basically we should not create lots of threads if we can do without it, okay. If we are doing it, then we are going to basically find problems when we scale, because there would be only a limited number of threads available in any VM. So we can't just infinitely go on increasing whenever a new connection, right? So, yeah. So this is, okay, all this is done, I think. So then there is the HTTP header called transfer encoding chunked. It came in HTTP 1.1. Okay, and how it comes into our picture. So we are not only doing that at the kernel level or the code level or the system design level, but also in the client or or wherever we are running our clients where we are making the HTTP connection. So there, this transfer encoding chunked header, it what it does is that it will allow the responses to come in the chunks to come in any order, and no content length header would be specified. Okay, so basically the server would be at the liberty to dynamically either end the connection whenever it wants. So basically it's a stream, right? So let's say you got a video, right? A video stream. So for example, what we are doing right now, right? Zoom. So we have started a meeting. I have shared my screen. So video is going on, right? So what it is doing is it's streaming to a particular client, for example, you. So it is not specified at particular response that what is the response size. There is no content length header. As and when I close it from my Zoom, your connection will also close, right? So that is how we are actually going on in reactive world as well. Okay, we don't know when our responses will come. It's asynchronous and non-blocking. So that is why we prefer to think in terms of streams instead of a single request response paradigm. Okay, and this happens in many websites as well. There is a infinite scroll, okay, or the connection, whenever the data is available, it is rendered. Connection remains open. Whenever data comes, it is rendered. In many um, front-end templates like theme leaf also, this behavior is used. So you open a connection, okay, data comes, data is rendered as and when it comes. You don't you don't wait for the response to come in entirety, right? So I hope I explained all of these things. Is there anything left? The stack here. So if we were to take the reactive stack, RDBMSs do not support reactive clients as of now. I mean, they don't give all those features. There is a very basic R2DBC from Spring, which is a reactive client for RDBMS. But since RDBMS are essentially or inherently blocking, all of those things cannot be done, which we are supposed to do in the reactive world. So they are inherently blocking. But still, they have done certain things. I used it R2DBC for a prototype, but I found it was severely lacking in many aspects. Then NoSQL databases, all of our NoSQL databases like Cassandra, Mongo, okay, Couchbase, Redis, they support reactive clients. Basically, they will give you an observable back, okay, and whenever data is available, it will trigger a callback that you have specified, okay, and you don't have to block anywhere. Then the languages, all of the languages that we have currently, Groovy, Ruby, Java, JavaScript, all of these things have already reactive paradigms. Either they are there natively. For example, in Java 9, we have it natively, and they have, if they don't have, then there is the RX extension. So this library on top of it, which you can use and make it react. Similarly, all the reactive, all the message brokers, Kafka, RabbitMQ, they also have clients with back pressure support. Okay, so if we come to Webflux is a Spring library, and what it is essentially using is Netty, and Netty is a runtime for reactive servers. So basically, it maintains a small number of threads, okay, and they actually use that. Okay, so I think I'm done with I think challenges are there. Some challenges are there. So challenges is, the first thing is that reactive programming is very difficult to debug. That is correct, because you don't have a simple flow that there's the same thread that is running everything in your code. Threads are changing, okay, and probably it's not a very good idea to use all those thread locals and etc. So basically, many things when they happen, there are lots of handlers and there are lots of uh, errors exceptions that can occur, which can be invisible to trace, because exception handling is again done in a different way. If there is a slight modification to what is the recommended practice, then it's a very going to difficult. Even like when we were doing the routing engine in the medicine pharmacy, there also we found that debugging is a pain actually. Then there's the steep learning curve of all these new concepts that you have to learn and understand before doing this. So I think we are out of time, but I can probably take, if you want, 2-3 minutes questions.
So one question, Zafar, the frameworks like React.js and React Native, are they also like based on the reactive paradigm?
React Native is not a reactive one. I mean, React Native is separate. It's just another platform for building UIs.
Yeah, but they do provide like async methods and all, right? The way.
Yeah. Since React Native is a built on top of JavaScript, so I mean the language that you use is actually JavaScript. So JavaScript essentially does everything in forms of callbacks and asynchronously only. So that is all asynchronous only, and it does give. So basically there is one thing called just callbacks, and then there's other thing called the observables that we were talking about. So observables are far richer. They are actually one level high from callbacks. Callbacks is the primitive way of handling the asynchronous flows, but observables, they are talking in terms of multiple callbacks in a stream of events. So basically, yeah, to answer your question, yes, there are observable libraries on top of React Native as well, JavaScript as well. So it's called RxJS.
Okay.
Okay, anyone else? Okay, I think if there are no more questions, we can wrap this up.
Yeah, I think session was really good. Feedback from my side. Really mind-bending kind of session.
Yep. Thanks, Zafar. It was a really nice session.
Okay.
Anyone who would like to volunteer for the next one?
We can do that offline as well. Okay.
Thanks, Jafar. Yeah.
Thanks, Zafar.
Thank you. Thanks a lot.